What if I told you that at the heart of a black hole there is a point where the laws of physics, every equation, every formula, everything science has ever built simply stops working? Welcome to the Cosmos in 5. Today we explore one of the most mysterious concepts in all of science, the singularity. What is a singularity? A singularity is a point in space where density becomes infinite, volume becomes zero, and the curvature of space-time becomes so extreme that our mathematical models break down completely. It's the center of a black hole, or at least what our current equations predict should be there. When physicists say infinite density, they don't mean really dense. They mean the math literally divides by zero. And in science, dividing by zero is a red flag that says our theory is incomplete. Think of it like this. Imagine a map of the world. As long as you are looking at Europe, America, or Asia, the map works fine. But walk to the geographic South Pole and try to draw which direction is south. There is no answer. Every direction is north. The map breaks down at that single point. A singularity is the south pole of physics. Our current map, Einstein's general relativity, our understanding of gravity simply cannot describe what happens there. How do singularities form? When a massive star collapses under its own gravity and forms a black hole, all that matter gets compressed towards the center. General relativity predicts it keeps compressing with nothing to stop it until it reaches a single point of infinite density. That point is the singularity. But physicists strongly suspect this is not what literally happens. It's more likely a sign that general relativity is the wrong tool for that scale, and that a theory of quantum gravity would describe the true behavior. There is another kind of singularity we don't know about. Big Bang singularity. When we trace the universe's expansion backward in time, everything converges to a single point of infinite density about 13.8 billion years ago. Again, our equations break down. We cannot describe what happened before or at the moment of the Big Bang using current physics. The Penrose-Hawking singularity theorems. In the 1960s and 70s, Roger Penrose and Stephen Hawking proved mathematically using general relativity that singularities are not just a quirk of idealized models. They are inevitable. If a sufficient amount of mass collapses in one place, a singularity must form. Penrose received the Nobel Prize in Physics in 2020 partly for this work. The universe is not just allowed to have singularities, it requires them. But here is what most scientists believe. Singularities are not physically real. They are symptoms of an incomplete theory. Quantum mechanics tells us that particles cannot be compressed to a true point. There is a fundamental limit to how small a region of space can be, called the Planck length, roughly 10 to the power of negative 35 meters. At those scales, quantum effects would dominate, and a quantum theory of gravity which we do not yet have would replace the infinite density with something finite and describable. Why does this matter for physics? The singularity is arguably the greatest challenge in theoretical physics today. Einstein's general relativity and quantum mechanics are both extraordinarily accurate theories, but they are fundamentally incompatible with each other at extreme scales. The singularity is where this incompatibility becomes impossible to ignore. Solving the singularity problem is essentially the same as finding the theory of everything, the grand unified framework that describes all of reality. So, here is what I want you to think about. If a singularity is a place where our understanding of the universe completely breaks down, does that mean there are things in the cosmos that science simply can never explain? Or is it just a matter of time before we build better equations? Let me know your thoughts below, and I will see you in next episode.